Delaware Tech, Chemistry 100, Chemistry 110, Solutions, Definitions and Properties. So a solution is a homogeneous mixture of two or more substances. It really doesn't matter what kind of substances they are. And they're composed of solute or solutes dissolved in a solvent. So whatever is dissolving in the other is called the solute. The one that is dissolving the others is called the solvent. And both the solutes and the solvents can be either solids, liquids, and gases. So the solute, again, is the substance dissolved in the other substance, in the solvent. And the solvent is the substance doing the dissolving. And how do you tell the difference between these two? Well, whichever one has more mass, that is by definition the solvent. And if you have 3 or 4 or 5 different substances homogeneously mixed, the one that has the most mass is by definition the solvent, and all the others are solutes. Solubility can be thought of as how well something can dissolve in a specific solvent under certain conditions of temperature and pressure. And in sciences, we like to be quantitative, so solubility is an actual value. It's an actual number that tells you the maximum amount of solute that can be dissolved in that solvent for that specific temperature and pressure. And we have several words that describe how much solubility has occurred, or how much solution has occurred relative to the maximum. Saturated means a solution that has the maximum amount of solute that can possibly be dissolved for that temperature and pressure. And unsaturated means anything less than the saturated level that is dissolved. That's unsaturated. But we have a third term, which is a little odd, called supersaturated. And supersaturated is a solution that temporarily has more than the usual maximum amount of dissolved solute. And we'll talk about how those can possibly be formed. It's a little weird to think about more than the maximum, but there is a way to do it. Concentration has many, many different units, and a general way to think about concentration is the amount of solute, and that can be measured by mass, by volume, or even by moles, relative to the amount of solvent or the total solution. And the solvent or total solution could be measured again by mass or volume or even by moles. So there are many different combinations, and some of these are even turned into percentages. We'll talk about several of these in this later in this unit. Colligative property. Colligative property are properties of solutions that depend only on how much solute is dissolved in the solvent. They do not depend on what the solute is, only how many particles of solute have actually dissolved. Now, some solutes will break up into more than one particle when they're dissolved, so we have to count the number of particles, but we're not really concerned with what those particles are when we're looking at colligative properties. One of those colligative properties is a concept called osmotic pressure. Osmotic pressure is the pressure required to stop a solvent from passing through a semi-permeable membrane. Okay, so if you have a solution of one type on one side of a membrane and the solution of another type on the other side of the membrane, whichever side has more solute dissolved in it, that's the side that the other one will try to flow into in order to dissolve it and in order to dilute it further. So if you have a membrane that only lets solvent through, solvent will always move from the more dilute to the more concentrated in an attempt to dilute the concentrated so that both sides are roughly the same concentration. And the more you have dissolved in one side, the harder it is to stop that, so the osmotic pressure goes up in those cases. So remember, a solution is any homogeneous mixture. So it doesn't matter whether they're solids, liquids, or gases. And we have gases dissolved in gases. Air is a perfect example of a homogeneous solution of gas dissolved in gas. And in fact, it's many gases dissolved in gas. We have The predominant gas in our air is nitrogen gas. About 78% of our air is nitrogen. Well, 21% is oxygen, the gas that we actually breathe. There's also a little less than 1% argon, and then there are trace amounts of other gases like water, carbon dioxide, ozone, chlorofluorocarbons, certain pollutants, etc. We also have solutions where liquid is the solvent. So we can have solid, liquid, or gases dissolved in liquids. As an example of solids in liquids would be salt water or sugar water. Liquid in liquid, antifreeze. Antifreeze is ethylene glycol dissolved in water. Ethylene glycol is also a liquid. Alcoholic beverages have ethanol in them, or ethyl alcohol. It means the same thing. Ethanol is a liquid on its own and can be mixed with water, and you make homogeneous solutions of liquid in liquid. We can also bubble gas into liquid to make solutions that way. Aerated water with oxygen or CO2 in water to make carbonated water. Those are gases in liquids. And oddly enough, we also have solutions where solids are the solvent. An example of solids dissolved in solids would be any alloy that has a homogeneous mix of more than two or more substances. Steel is about 1% carbon evenly distributed, homogeneously distributed in iron. Brass is zinc dissolved in copper. We also have liquid in solid solutions. There's a material called amalgam. Amalgams are metals that are dissolved with mercury. And if you have more of the solid metal than the liquid mercury, we would say the liquid is dissolved in the solid. If we had more mercury, we would say the solid's dissolved in the liquid. But mercury can dissolve a number of metals, including silver and gold. And in fact, for years and years, dentists would use an amalgam of mercury in silver to pack into the holes after you drilled the teeth to remove the cavity. We also have gases in solids. If you have a very porous form of certain metals like palladium or platinum or even nickel, you can bubble in hydrogen gas, and the hydrogen gas will evenly distribute within the metal. So that would be a gas in solid solution. So you can get all combinations for solutions. So let's talk about some of the definitions related to saturation. Unsaturated solutions have less than the maximum amount of solute dissolved for that temperature and pressure. So in this example here, we see that 20 grams of sodium chloride in 100 mils of water is less than the maximum you can dissolve in the water. In B, you see that we have 36 grams of sodium chloride in 100 grams of water. That's the most you can dissolve for that particular temperature and pressure. And if you add any more, like in the last case where we have 45 grams, well, only the 36 stay in solution. The other 9 are just sitting at the bottom. So one way you can tell you have a saturated solution is that there's extra that didn't dissolve sitting on the bottom, and now you know for sure it's saturated. Saturated solutions obviously have the maximum amount that is dissolved. So that would be in the case of B or C, those are saturated. And I also told you about supersaturated solutions. They have more than the maximum amount of solvent dissolved, which is a weird thing to say, but they have to be made very carefully because they're extremely unstable. And the way you would make them is you start off with your solvent, and you begin adding solute to it until you reach a saturated point. So in this particular experiment, we start at 25 degrees C, and we throw in our solute. It doesn't really matter what the solute is. Let's say it's some salt. And maybe only 91 grams of the 100 grams you put in will dissolve. That's a lot of material. We have 91 grams dissolved in there, and 9 grams are sitting at the bottom. They just will not go in at 25 degrees C. We're saturated. That's the most you can get in. And then this is a dynamic equilibrium, meaning that some of that 91 will come out of solution and fall to the bottom, and some of that 9 will go into solution, but at any one time there's 91 grams in solution. And then we heat it up. That's what that little triangle means. That means we're heating it up, and we heat it up to 50 degrees C. So now our maximum saturation level is actually higher. So we can get all 100 grams to solution at 50 degrees. That's no problem. In fact, it's actually below the solubility for that temperature. But now here's the tricky part. You cool your solution from 50 back down to 25 extremely slowly and extremely carefully. You don't touch the beaker or the container. You don't shake the room. You even have to be careful how you walk around nearby so that nothing vibrates, and you're using a smooth container that has no nicks on the walls to let crystals start forming. And if you let it cool slowly enough and gently enough, all of that 100 grams will remain in solution even at 25 degrees. And there's a reason for this that's somewhat complicated to explain, related to the thermodynamics of the solution. I won't go into it. But the fact is, you're kind of, quote unquote, fooling the solution to keep that extra amount in at a lower temperature. And then if you literally just touched the glass, picked it up, bumped it, tapped a pencil against the glass, instantly 9 grams would come back out of solution, what we call precipitating, what we colloquially call drop out of solution or fall out of solution. Precipitate would be the correct word, and that 9 grams would come back out, and we would go back to our normal saturated solution of 91 grams in the water or whatever solvent we're using. So let's talk about factors that affect total solubility, the actual solubility, the actual maximum amount you can dissolve for that for those conditions. And the first rule is that for solids dissolved in liquids, as the temperature goes up, the solubility goes up. In other words, we warm it up, we can put more in solution. And this happens for almost every solid. There are only a couple of exceptions. And think about dissolving more salt or more sugar in warm water. It's easier to do that than in cold water. And let's look at this chart here. You can see there's a lot of things on this chart. So this is a chart of grams of solute per 100 grams of water. In other words, the solubility. So high level means it's very soluble, a low level means it's not so soluble, and then our x-axis is temperature, and we're going from low temperature to high temperature. And I'm just going to circle the substances that are solids in this diagram, and we can look at these curves only for now. And the nice thing about this is they're color-coded, and then there's one more right here. And you can see that every one that I circled, these are solids, and you can see that even if the shape is a straight line or a curve, they all go up, some only gently, like sodium chloride, but some go up dramatically, like potassium nitrate, KNO3. So they have increased solubility with increased temperature for these solids. For gases, however, it's the opposite effect. So be very careful when you're thinking about solubility. For gases, when the temperature goes up, the solubility actually goes down. And I'll circle the gases in here. Oh, I left out one solid last time, Ki. When the gases are increased in temperature, it's harder to dissolve them. And here are the 3 gases on this chart. Hydrogen chloride gas, which dissolved in water becomes hydrochloric acid. NH3, which is ammonia, which dissolved in water can make some ammonium hydroxide. And SO2, which dissolved in water can make sulfurous acid. So each of these 3 are gases, and you notice that for each of these 3, the curve goes down when we increase the temperature. And one way to think about that in everyday life is that when you have warm soda, it tends to be flat. It tends to be flat because the carbon dioxide gas starts coming out of solution. The gas is not as soluble in the soda when it's warm soda than when it's cold soda. And then the third concept is related to pressure. Pressure doesn't really affect the solubility of solids or liquids very much, but gases, it can dramatically increase their solubility as you increase pressure. This is actually called Henry's law. There's a very simple formula for this, which we won't go over, but the idea is that as you increase pressure, you're literally pushing gas into the solution. You can just think of it as a piston pressing the gas down, as shown in this diagram, so you get more gas molecules actually driven into the liquid, increasing their solubility. So soda under pressure has more carbonation. We all know that if we leave a can of soda open to the atmosphere, where there's no high pressure pushed on the soda inside the can, the gas in the soda, the carbonation, will come out. The carbon dioxide will come out of solution over time. And again, your soda will go flat. So these are all things you've already seen in everyday life. So now let's talk about factors that affect how fast you can dissolve things, the speed of solubilization. So temperature, just like before, can affect the overall solubility, but can also make things go into solution much faster. We all know that if we heat something up, it'll go in solution faster. Yes, it will also increase the solubility of solids, but it also makes it faster to get those solids dissolved. Stirring also helps. And the reason why stirring helps is, think of the crystals or whatever solid you're putting in the liquid. It might be a large chunk. In order to dissolve it, the water or whatever solvent is being used has to surround individual particles. In other words, particles from your larger particle that you put in the solvent must be broken apart from the large particle over time. And one way to do that faster is to stir it, so you're always bringing fresh solvent next to that crystal to allow it to break apart faster and faster. In fact, we can also chop up our particles beforehand. We can grind our big chunks of whatever we're dissolving into a fine powder to give it more surface area, because smaller particles will dissolve much faster because they're closer to being the smallest particles that need to be surrounded by solvent molecules. So if you start with small particles, it'll go faster. We all know that if we put a giant chunk of salt in water, it's going to take longer to dissolve than if we ground up the salt into little tiny crystals and then dissolved it in the water. So let's talk about electrolytes. Electrolytes are substances that break up into ions when they're dissolved. In fact, the electrolytes are the ions. So pretty much all ionic compounds, which are composed of ions by definition, most of these are metal salts, some are ammonium salts, as well as a lot of acids, especially the strong acids, break up into ions the second they go into water. And those ions are just called electrolytes. They're called electrolytes because they're charged and because they can be used to carry electricity. If you have salt in water, that water can conduct electricity a lot better than just pure water. A non-electrolyte is a compound that doesn't separate into ions when you dissolve it. So most covalent compounds are non-electrolytes. Most sugars don't break apart. If I threw in sucrose into water, it doesn't break apart like, say, sodium chloride. If I threw a salt like sodium chloride in, I would get sodium ions and I would get chloride ions. Those are electrolytes. But if I threw in glucose or sucrose or any other sugar or alcohols like ethanol or methanol, they don't break apart. They just get individually surrounded by the water in the solution and stay uncharged, so they're called non-electrolytes. So strong electrolytes are electrolytes that dissociate completely. So sodium chloride is a strong electrolyte. When you put sodium chloride in water, 100% of it, if it's dissolved, 100% of it will split up into sodium ions, Na+, and chloride ions, Cl-. All of it goes into solution, breaking up into individual ions. So the word strong here has nothing to do with concentration. It doesn't tell you how much we put in. A strong electrolyte is one that completely separates, whereas a weak electrolyte would be one that doesn't separate very well. There are some ionic compounds that aren't very soluble, and only a tiny fraction will break up into ions and dissolve in water, and the rest of it will just drop to the bottom of the water and not dissolve. Those would be weak electrolytes. So strong in this case, in chemistry, strong means easily dissociated. And when we get to acids, it actually has the same meaning. Another example would be magnesium nitrate. Nitrate salts are almost always soluble in water, highly soluble. So it will break up into each one of these formula units will break up into one magnesium ion, Mg+2, and two nitrate ions. And it will go pretty much to completion. 100% will go all the way to these three ions. So that is another strong electrolyte. And another concept I want to talk about is how well two liquids mix together. And if they mix together extremely well, in other words, they don't form layers, that's called miscible. So the technical word is miscible, and it's quite related to the word mixable. In fact, they have the same word origin. So when you hear miscible, just think mixable. So what's mixable? Well, water and ethanol. Ethanol is a very small organic molecule. Most organic molecules do not dissolve in water, but ethanol is very small, and it has a hydroxyl group on it, an OH group on it, and so it can form hydrogen bonds with water. So it's very stable, dissolved in water, and you can make ethanol solutions up to very high concentrations. Oil and gasoline, these are both nonpolar materials, nonpolar liquids, and they will mix very well. So polar and polar love to be together, like water and ethanol, or other polar solvents or liquids. And nonpolars like oil and gasoline also will mix together well, so they are miscible. So what does immiscible mean? Well, immiscible means they can't mix together well, and you end up forming what we call phases. So miscible liquids will form only one phase, but immiscible liquids are not mixable. So immiscible means unmixable. And again, they have the same root words. So you can see in this diagram here, we have some kind of mixture of two liquids that will not dissolve in each other, and they separate. And the lighter one, the one with less density, will be on the top. That would be the yellow one in this case. And the green one would be the more dense. And I suspect what this is green dye in just water, and some kind of yellow dye that is in some type of fatty liquid, maybe oil, maybe a grease, maybe an organic solvent, probably an organic solvent, that was dyed yellow so you could see the two layers. Frequently you'll do these mixtures in the lab and both layers will be clear, but if you look carefully you can see the little lines separating them. So oil and vinegar is a very famous immiscible mixture. The oil is less dense than the vinegar, and if you put them together and you don't shake them real hard and you don't add something to help them mix together called emulsifiers, they will separate, and the oil will sit on the top and the vinegar will sit on the bottom. So any oil and water mixtures, this could be motor oil and water. If you ever go outside and you see puddles sitting underneath an old car, there might be water and oil in that puddle. Well, the oil will be floating on top of the water. And in fact, most organic solvents mixed with aqueous solutions, that is solutions that have water, are immiscible. And we'll stop here.